Hello viewers, my name is Dr. Kishen Ajay, Department of ECE, Institute of Aeronautical Engineering College, Hyderabad. So today we are going to discuss about the problems on YAGI UDA and helical antenna. So this topic is related to the course Antennas, Waves and Propagation. So today's topic is problems on YAGI UDA antenna, and also let us discuss a few problems on a helical antenna. These topics are related to the course Antennas, Waves and Propagation. So let us start our session today. So here, before going to discuss about the YAGI UDA antenna, so we know that in a YAGI UDA antenna, to design a YAGI UDA antenna, so we need basic, there are three basic requirements. One is the dipole antenna, the other one is the reflector antenna, the others are directors. So this is the basic design of an YAGI UDA antenna. So if we want to design an YAGI UDA antenna, so we need to know the length of the dipole, we need to know the length of the reflector antenna, and we need to know the length of the directors. So minimum of 2 directors and a maximum of 40 directors can be placed for the design of YAGI UDA antenna. So here generally the basic requirements of whenever we are going to design a YAGI UDA antenna, so there are some predefined values given for us for the design of YAGI UDA antenna. That means how much must be the length of the dipole, how much must be the length of the reflector antenna, how much must be the length of director 1, director 2 and the director 3. So basically this YAGI UDA have given us some basic specifications for the designing of this antenna. So generally when we design an YAGI UDA antenna, the length of the dipole must be equivalent to 143 by f megahertz. So the length of the dipole must be equivalent to 143 by f megahertz. So this is, let us assume this as LD as the length of the dipole. So we know that this is the dipole antenna and this is the reflector and this is the director. So this is, let us assume this as the director 1, this as the dipole antenna and this as the reflector antenna. So the length of the dipole must be equivalent to 143 by f megahertz. This L is measured in terms of meters. Measured in terms of meters. Similarly, the length of the reflector must be equivalent to 152 by f megahertz, and this length is also specified in meter. So this is the length of the reflector indicated as LR. This is LD. And similarly, the length of the director 1 is denoted as LD1. The length of the director is always less than the length of the dipole and also the reflector antenna. So it is given as 137 by f meter. So these are the standard specifications for the design of YAGI UDA antenna. There is the length of the dipole is over 143 by f. The length of the reflector must be 152 by f. The length of the director 1 can be 137 by f. Similarly, the length of director 2 it is given as 133 by f. And similarly, the length of director 3 is equal to 130 by f. And the length of director 4 is given as 127 by f. So here, whenever we design antenna, we need to know the length of the directors D1, D2, this is D3 and this is D4. So these are known as the lengths, predefined length of the YAGI UDA antenna. So how many number of directors we place, it depends upon the design, and each director will be less than 2.5% of the previous one. Suppose if the length of the director 1 is equal to 10 meters, the length of the D2 will be 7.5. Similarly, the length of D3 will be, it is 5 meters. So here, the basic standard rule is that the length of the subsequent directors must be less than 2.5%, of the previous director. So this is we are going to use this rule for designing of a YAGI UDA antenna. So these are the basically the predefined the lengths, predefined lengths of a dipole, reflector and director. Similarly, there must be some spacing between the length of the reflector and the length of the dipole. And there is some spacing between the length of the dipole and the length of the director 1. So what must be the length between the director 1 and director 2? So there are some standard specifications again for us predefined values here. We need to use those values for the design of YAGI UDA antenna. So here, so if this is the reflector antenna and if this is the dipole antenna, this is known as a spacing, and this spacing, the reflector between the director is given as 75 by f megahertz. Similarly, if this is the director 1 and this is the dipole, the spacing between the dipole and the director 1 is given by 40 by f megahertz. Similarly, the spacing between the dipole and the director 2, it is given as 38 by f megahertz. It is given as 38 by f megahertz. So these are the standard spacings between the reflector and the dipole antenna, the dipole and the director 1, and also the director 1 and the director 2. Now let us calculate the length of the dipole. The first problem, it is given as calculate the length of the dipole, the reflector, the director 1, the director 2, the director 3 of a YAGI UDA antenna with spacing between the elements whose operating frequency is 177.5 MHz. So here we need to calculate, design how many directors are there in the given problem. There are 4 directors and 1 dipole antenna and there is 1 reflector antenna. So totally we are going to design a 6-element array. We are going to design a 6-element YAGI UDA antenna. So design a 6-element YAGI UDA antenna with operating frequency of 177.5 MHz. So let us calculate this by using the formula. So we have defined some formula here. So based upon this formula, we are going to find out each of the lengths of the dipole, the reflector, the director 1, the director 2, the director 3. So we are going to design a 6-element YAGI UDA antenna. So now let us find out the length of the dipole 1 first. We are applying the formula 143 by f megahertz. So we know the formula, the length of the dipole, it is given as 143 by f. So 143 by f is nothing but 143 by, it is given as the frequency 177.5. So this is equal to, if we simplify this, we will get 0.8 meters. So this is the length of the dipole. Similarly, we are going to find out the length of the reflector. The length of the reflector is given as 152 by f. If we calculate this 152 by 177.5, you will get 0.86 meters. So we will get 0.86 meters. So similarly, we are going to find out the length of the director 1. So the length of the director 1, it is given as, the formula is 137 by f. So 137 by f is equal to 137 divided by 177.5. So this is equal to 0.75 meters. So 0.75 meters. Similarly, the length of the director 2, the formula is given as 133 by f. The length of director 2 is given by 133 by f. 133 by 177.5 is equal to 0.75 meters. So this is 0.77 meters. Similarly, the length of director 3, it is given by 130 by f is equal to 130 by 177.5 is equal to 0.73 meters. So we have found out the length of the director, the dipole, the length of the reflector. This is LD1, LD2, LD3. So this is 1, 2, 3. This is director 1, dipole. This is the reflector. Now we need to find out the spacing between the elements. We need to find out the spacing between the elements. So what is the spacing between these two elements? So the spacing between, now let us find out the spacing between the reflector and the dipole. The spacing between the reflector and the dipole is given as 75 by f megahertz. So 75, it is nothing but 75 divided by 177.5 megahertz. So 77 by 177.5 you will get 0.42 meters. 0.42 meters. Now the spacing between the dipole antenna and the director one. The dipole antenna on the director one, it is given as 40 by f megahertz. So 40 by 177.5. So this you will get 0.23 meters. You will get 0.23 meters. Similarly, the spacing between the directors, the spacing between the directors is given as 38 by f megahertz. So 38 by f is equal to 38 divided by 177.5 is equal to 0.21 meters. 0.21 meters. Similarly, you can find out the values between D2 and D3 as 38 by f is equal to 0.21 meters. So like this, we need to find out a 6-element array, the length of the reflector, the length of the dipole, the length of the director 1, the length of director 2, director 3, and also we need to find out the spacing between the reflector and the dipole antenna, the dipole and the director 1, the director 1 and the director 2 spacing. So after finally finding out the values, we need to indicate all those values in the form of a figure. We need to represent in the figure. So like this, we need to represent the spacing. So finally, what we need to do is, so we need to draw the dipole antenna, we need to draw the reflector, the director 1, director 2 and director 3. So the spacing is between these is 0.42. So we need to represent here, and this is 0.23 and this is 0.21. The spacing is, and the spacing is here 0.21 here. So similarly, you can find out, represent here the length as the reflector 0.77. This is 0.75 meters and 0.73 meters. This is the length of the reflector. How much? This is the 77 meters. So like this, we need to represent all the elements. We need to represent all the values for the design of YAGI UDA antenna. So you can see on the screen here, the length of the dipole is given as L is equal to 143 by f. It is represented as 143 by 177.5 is equal to 0.80 meters. The length of the reflector is 0.86 meters here. The length of the is 0.80 and 0.86 here. This is 0.86 here. 0.86 and this is 0.80 here. Similarly, the length of director 1 is given as 137 by f, it is 0.77 meters. The length of director 2 is given as 133 by f, that is equal to 133 by 177.5 is equal to 0.75 meters. The length of director 3 is equal to 130 by f is equal to 130 by 177.5 is equal to 0.73 meters. So this is the spacing between the reflector and the dipole. Between the dipole and the director 1, 40 by f. Director 1, director 2 is equal to 38 by f megahertz. So 38 by 177.5 is equal to 0.21 meters. Now let us do similarly the second problem also. So design an YAGI UDA antenna of 6 elements if operating frequency is 200 megahertz. If operating frequency is 200 megahertz. So similarly as how we have the earlier one, we need to find out this the same thing by using the formula. So we know that 143 by f, the length of dipole is, so 143 by 200 is equal to 0.715 meters. If there are 6 elements, there will be 4 directors. So for the 6 elements, there will be 4 directors, 1 dipole antenna and 1 reflector antenna. So the total is 6 here. So design YAGI UDA antenna of 6 elements whose operating frequency is 200 megahertz. So we need to find out the values of 4 directors, the length of 4 directors individually. So the length of the dipole is given as 143 by 200. The length of the reflector is given by 152 by 200 0.76 meters. The length of diameter 1 is given by 137 by f is equal to 137 by 200 is equal to 0.685 meters. So similarly, the diameter 2 is 133 by f. The length of diameter 3 is given by 130 by f. So f is nothing but the given frequency, that is 200 megahertz. We need to substitute. So 130 by 200 is equal to 0.65 meters. And similarly, the length of diameter 4 is given by 126 by 200. It is if we simplify this, we'll get 0.63 meters. Similarly, the spacing between the reflector and the dipole is given by 75 by f. So 75 by 200 is equal to 0.375 meters. And the spacing between the dipole antenna or the driven element and the direct element is given by 93 by f is equal to 93 by 200 is equal to 0.465 meters. Now let us do a problem on a helical antenna. Here, for a 20-turn helical antenna operating at 3 GHz frequency with circumference C is equal to 10 centimeters and the spacing between the turns is 0.3 lambda and the spacing between the turns is 0.3 lambda, calculate the directivity and half power beam width here. So here, according to the given data, so the number of turns given is given as n is equal to 20 here, number of turns. The frequency is given as 3 GHz here. The circumference C is given as 10 centimeters. And the spacing between the turns it is given as 0.3 lambda. So we need to find out the directivity and half power beam width. So from the given data, so we need to find out the directivity and the half power beam width. So what is directivity here? The formula for directivity is given by 15 NS C square by lambda cubed. So if we simplify this, you will get 15 into the n value is 20 here. The spacing is given as 0.3 lambda into C square is equal to 10 into 10 power minus 2 whole square. So we need to find out this in meters, 10 into 10 power minus 2 meters here. Whole divided by lambda cubed. So whole divided by lambda cubed. So we need to find out, substitute all the given values in the problem. So after substituting all the values in the problem, you will get the value of, we need to find out the lambda value also. So lambda is equal to C by F, we know that. What is C? C is the velocity of light, 3 into 10 power 8. And what is the lambda value? The frequency given is 3 GHz, 3 into 10 power 9. So you will get 1 by 10. So lambda is equal to 0.1. So you can substitute this lambda as 0.1 whole cube. Substitute this lambda value as 0.1 whole cube. So if you simplify all these, substituting all these values, and if you simplify, you will get as 90. You will get the value as 90. So GD is equal to 90. And you can also, this is the decimal value. You can also convert this decimal value into decibels also. So GD is nothing but GD max. So the maximum directivity is known as directivity. GD max is nothing but directivity. The directivity is defined as, the definition for directivity is the maximum directive gain is known as directivity is equal to 90. So this is decimal value. You can also convert this directivity value into dB by converting as 10 log 90 base 10. So then we will get in the value in dB here. Similarly, we can find out the value of half power beam width. So half power beam width HPBW is equal to 52 by C root of lambda cubed by NS. So 52, what is 52? The decimal value. C is given as 10 into 10 power minus 2 here. Root of lambda cubed. So what is lambda here? We are getting lambda as 0.1. So 0.1 whole cubed divided by NS. N means 20 here, number of turns. The spacing it is given as 0.3 lambda. 0.3 into lambda value is 0.1 here. So if you substitute and simplify, you will get 21.23 degrees centigrade. So you get 21.23 degrees centigrade. So this is how to simplify the problem. That is, for a given data, so all the data will be given in the problem. That is 20 turns helical antenna. This is helical antenna, you can see here. The number of turns is equal to 20 here, and the spacing between the turns is given as 0.3 lambda here, and the circumference, this is the circumference, is given as 10 centimeters. The operating frequency is given as 3 gigahertz. So for this we need to find out the directivity and half power beamwidth by applying this formula. So you can apply this formula to find out the problem here. So you can do the GD max value. So you can see in the screen, you will get half of beamwidth as 21.23 degrees. So for references, you can for these problems you can refer Antennas and Ray Propagation by UA Bakshi, by KD Prasad, or Satya Prakashan and Antennas and Propagation. So for these problems you can refer the Bakshi. You can also refer the Antennas and Propagation by KD Prasad, or you can also refer the another book by name Cross, John D. Cross, for reference. Or also another textbook is there, Balanis. So these are the standard textbooks. For more problems, you can refer the John D. Cross and the Balanis textbooks. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.